Okay. Oh. Let's go on. So oops. Okay. So here are the equations about the average magnetic moment and the moment along the z direction mu z. So in shown here is a detailed equation of the g factor. Okay, we call it, this is called lambda g factor. So in the beginning, we just say that for the orbital angular momentum, that the g factor is equal to 1, and for the spin angular momentum, the g factor is equal to 2, and the s is the spin angular momentum, and L is the orbital angular momentums. So you can imagine that if they are solely orbital angular momentum, then the s would be equal 0, right? And the j is equal to L plus s. So in this case, if we have no spin angular momentums, then j plus 1 will equal to L plus 1. And in this case, this one and this one are identical. So the numerator would be eliminated, and this form would be equal 0, and the g will left 1. So that's the reason why the pure orbital angular momentum will give you the g vector like 1. In contrast, if we have only spin angular momentum, then the L will be equal 0. And in this case, the j will be equal to s. So this is s plus 1, and this is also s plus 1. And in the denominator, here is would be 2 times s plus 1. So the numerator and denominator are also all 2 s plus 1, and this form would be equal to 1. So 1 plus 1 would be give you the g factor is equal to. So this is also the reason that why the spin moment or spin angular momentum will give you the g factor is equal to. Okay. But in some case, if the s or L are not 0 value, then you will get the g factor in between 1 over 2. Okay, so fortunately, when we calculate the 3D electron, the magnetic moment that comes from the 3D electron, we don't need to worry about the L. So the g factor would be always use 2. Okay. That would be much easier for us to estimate all kind of the usual 3D transition method. Okay. So the analog expression for the electron intrinsic angular momentum or spin, we can write a similar form like this. Okay, so I don't want to repeat that again, but here we need to use the g factor is equal to 2. Okay, shown here the spin quantum number s is equal to 1/2. So the ms would be the same, only two value, minus 1/2 and 1/2. And both ml and ms will vary in the integral step. So if the one spin angular momentum is minus 1/2, and the other it would be 1/2, because the step would be 1. Okay, that would be integral steps. Okay, similarly, the total angular momentums is the vector sum of orbital and the spins. So we will get the j have identical form, but just substitute the L or S to j. So the average magnetic moment comes from the total angular momentum would be root square j plus 1 h bar, and the j value would be in between the L minus s to L plus s. And the z component of the mj would be zero component of the angular momentum would be mj h bar, and the mj would be in between the minus j and the plus j that we already talked about in the previous slide. Okay, this is for the one orbital electrons. For the many electron atoms, they have a similar form, but we just substitute the J to capital J, which represent the sum of the Js. So this is the typical form, so I don't want to repeat that again. So the total angular momentum includes spins. J can be integral or half integral, depending on whether the atom has even or odd number of electrons respectively. And then the G factor is also the same in that case. So we can imagine that if a dipole moment mu placed in an external magnetic field B, and this magnetic field is pointing in the z directions, then this magnetic moment will experience a torque N given by the vector products N is equal to mu cross B, and the average magnetic moment along the z direction would be like the equation here. Okay, wait a moment. So we just ignore a lot of the directive from statistical thermodynamics. I just give you the result. The average magnetic moment is equal to G mu Bj of eta. Here the Bj of eta is the a function that correlates with the J value. So the Bj of eta is equal to this form, which is called the Brion function, and this function is the J dependence equation. And in this case, the Brion function will have two extreme values, 0 and 1. For the extreme case, so it's shown here is the Brion function will be in between the 0 and 1, but the curvature would be varied with different J values. So this is the case for the J equal to one half, and this is the J value when it equal to 1, and this is equal to 7/2. Although the curvature are different, but the maximum values are all identical. They are all 1, and the minimum value is also are all 0. Okay, so which means this case for the average magnetic moment along the z direction, this value would be in between the 0 over G mu Bj. So for the so let's examine the behavior of the Bj of eta for the large and small value of its argument. So for the eta relative larger than 1, the hyperbolic tangent approach to 1 unitary, and this equation will be approach 1. So what does that mean? That means for the saturated magnetization, the mu z would be equal to G mu Bj. So what does that mean? This is the mathematic form of the explanation of the paramagnetism. But in the practical, you can imagine that if you want to make a large, if you want to make a magnet which contains a large magnetic field or magnetic moment, you may choose the material that have a large J, because G value will be fixed by J, and the mu B is the constant. So what kind of material will carries large J? In 3D transition metal, the J value is equal to the S value, right? So when we go back to the periodic table, okay, shown here. Let me just enlarge the periodic table here. oops, a little bit. So I will highlight the periodic table here. Okay, you can imagine that if you want to create very large magnetic moment, you need a very large spin number, total spin number, right? Because for the 3D transition metal, the J value here is equal to S value. If you have a very large S, which means you will have very large average mu Z, right? And so here, where can you find the very large S? Don't forget about that. The spin will cancel to each other if the spin direction is in if the spin in one orbital is in opposite direction. So we cannot find a case like this one if we have 10 electron spins, but they are all anti-parallel. It will give you S equals 0. That's not the case we want to find. So we want to find the case is we have a lot of lonely spin, right? They are not a pair spin. They are solely one in an orbit. So in that case, we were looking for the spins like this one. Oops. So this is the case for the trivalent ion. So the electron configuration of ion is like this one. So they have 3d6, 4s2, and when we remove 3 electrons from the octal, we just eliminate 2 from the 4s octal and remove 1 from here. So we will get 5 parallel spin of the electron in the orbital. So this one will give you the maximum magnetic moment along the z-axis. So we can also find a similar case in the divalent magnets, right? So divalent magnets will also have the electron configuration about the AR 3D5. Okay, we can also find similar things in the cobalt. So in the cobalt case, we may find the tetravalent that we need to remove 4 electrons from the cobalt, but that's very rare because the cobalt do not have the tetravalent case. Okay, so the most probable or most useful metal that will give you the large magnetic moment is the ion and the magnets. Okay, that's the reason the most useful magnet is made by the ion or magnets. Of course, sometimes we will use the cobalt and the nickel, but the cobalt and the nickel will have less saturation magnetic moment than the ions. By the way, the cobalt is much expensive than the ions. So these 3 elements will be very useful for make a magnet. Sometimes we will use a magnet, but the only one problem is the magnetic ordering of the magnets is at a very low temperature, not like the ion, cobalt, and the nickel. So when you go to the bookstore and buy a magnet, typically the black one is made by the ferrite, which contains the trivalent ions. Okay, so that's the expression about the usage of these equations. So once if you want to talk with the material scientist, what kind of the material you need to choose to make a good magnet? you need to looking for a good J value of good J value. Choose the good J value in the periodic table. Of course, we just talk about the element that at the 3D transition method, but you can also looking for the magnet in the real Earth element. So where is the real Earth element? We will go back to the very early PowerPoint slide here. Okay. So in this slide, here is the real Earth elements, which called the length lines. Okay. So in this case, these real Earth elements that will give you a large J, and in this case we have electron configuration that contains 4 F electrons, and the F electron have no phenomena like the 3D electrons. The orbital change would not appear in the 4F orbital. Furthermore, the F orbitals give you the error is equal 3. That would be very large value. So you will find another magnet you can buy from the bookstore is the the color like metal, is the silver white color. That kind of magnet is made by the neodymium. Okay, neodymium boron ion is a very strong magnet. The field strength would be 8 to 10 times than made by the ion. So if you want to make a very, very strong magnet, you need to looking for the element from the length lines. Of course, you don't want to make this magnet by the element the artisan here, because they are all radiation element. You want to put the radioactive elements near to your body, right? So the best way to looking for the strong magnet is make this magnet by the element at the lengthening element. Okay, so that's the example that if you have a basic knowledge about the magnetic theory, then you can know where to look the material or compound that fit your usage. Okay, let's go back to the paramagnetism. Okay, this is the knowledge about the saturation magnetization, and in another way, we can find here is if we got a small value of the y is the value that means that we have the very, very close to the 0. So in this case, the hyperbolic potential would be equal to 1 over y plus y over 3, and in the end we will get the average mu z is equal to these equations, and these equations there are constants here, g, mu b, j, and k are all constants. So we can rewrite this equation like this way. So if we sum all of the mu z and divide it by the volume, we will get the volume magnetization. And the volume magnetization is look like this way. And if we put this parameter as a constant c, then we will get a relation like m is equal to cb by t. And in these equations, this is typical called the Curie law, which was discovered by the Pierre Curie. He is the husband of the Marie Curie. Okay, so he found the magnetization of the paramagnetic solid is proportional to the ratio of the magnetic field and the temperature, and to the temperature. Any questions? No? Okay. So let me give me a very brief idea. What is the definition of the what is the definition of the high temperature or low temperature, or the what is called the high magnetic field or low magnetic field? So in the typical case, if we apply the 1 Tesla magnetic field, so the 1 Tesla, let me give you an idea. The magnetic field created by Earth in the Zhongli area is about the probably 0.4 Gauss, and 1 Gauss is 10 to the minus 4 Tesla. So that means the magnetic field created by Earth in Zhongli area is about 4 times 10 to the minus 5 Tesla. Okay, so that would be very weak. And typical magnet, I mean the brake pellet magnet, the magnetic field on its surface would be about the 500 Gauss, which is 0.05 Tesla. And for a neodymium boron ion magnet, which is the one that I just mentioned about the silver white magnet, in that case, this magnetic field on its surface is about 0.4 Tesla. So 1 Tesla is really a large magnetic field. And in this case, the 1 Tesla magnetic field, and in the ambient temperature, which is 300 K, and the G factor is equal to, then we can calculate the G mu B value is about 4.4 times 10 to the minus 3. That would be thousandths, 1 over thousandths, then 1. Okay, so the Curie law would be applied in these conditions. So when you want to measure the magnetic moment or the Tc of the material at the room temperature, this value is very safe to measure the property of the magnetic material. But in another case, when we go to the low temperature, which is about 3K, and if we have the same G value and the J is equal to 1/2, and the magnetic field is also equal to 1, then we will get the magnetic moment along the average magnetic moment along the Z-axis is almost saturated, which is 75%. 75% then is saturated 1. Okay, so you do not hear the microphone since the beginning of this class, right? Okay, so do you hear my voice? Okay, so what time do you miss my voice? 1 minute before? Okay, okay, no matter what, let's keep going. Okay, so okay, I will repeat this slide again. So for the typical case, if we have a 1 Tesla magnetic field, which is almost twice stress than the loss of the silver white magnet or neodymium ion boron magnet. And we also put the sample in the ambient temperature, which is 300 K, and the G value is equal to. Then we will get the parameter G mu B by KT is about 4.4 times 10 to the minus 3, which is very small value. And in this small value, we would apply the Curie law to estimate the magnetic moment and the critical temperature. But when we go to the very low temperature, about 3K, and if the G value is equal to and the J is equal to 1/2, and the field, when we apply the field is about 1 Tesla, then we will get almost 75% saturate, which means it's only 25% less than the saturation magnetization. So the behavior of those paramagnetism is quite different at the high temperature and the low temperature. Okay, so let's give you an idea for the practical cases. Okay, for example, if we have a paramagnetic cell, and we can define the paramagnetic cell is the ions that contains paramagnetic ions surrounded by a large number of non-magnetic particles. So typically is the Cr2 SO4 3 times K2 SO4 times 24 H2O. So this is chromium, potassium, aluminum. And for this case, the magnetic property is due solely to the chromium atoms. So chromium atom contains 3D ions, and all the others have no 3D electrons. So we can, in this case, we know the chromium is trivalent, so they have unpaired electron spins, and the magnetic moment is 3 mu b, just as that I show you in my whiteboard. Okay, besides these 2 chromium ions, there are 4 sapphire atoms, 2 potassium atoms, 40 oxygen atoms, and 48 hydrogen atoms. So they are all non-magnetic. So in this case, that means the 2 chromium ion is very dilute inside the crystalline, because they are total 94 particles are non-magnetic, and the interaction between the magnetic ion would be very weak because they are dilute in the 2 chromium is dilute in 49 particles, which means the interspace between these 2 chromium would be spaced by 47 particles in average. So that would be very large distance, so we can ignore the interaction between these 2 chromium ions. So they will only react to the magnetic field that from the external, and not the internal interaction between the chromium ions. Furthermore, we also know the orbital motion, the valence electron is quenched by the field of the neighborhood in ions, so we only need to count the spin angular momentum. So we can calculate from here. So the electron configuration of the chromium atom is like this. So we can write this would be AR 4s1 3d5, and in this case, you know this representation means that argon have 18 electrons in cross shell. So the chromium have additional 6 electrons, 1 in 4s and the 5 in 3d subshell. And the chromium, the trivalent chromium will remove 1 4s electron and the 2 3d electrons. So the electron configuration will be like this one, the AR3D3. So in this case, this 3d electron will produce paramagnetism. Okay, so the total angular momentums, okay, orbital angular momentum is essentially 0. So the J is L plus S, and L is equal to 0. And the S with have 3 electron spins contains 1/2 magnetic moment. So we have the total sum of the magnetic moment is equal to 3/2. With the G value is equal to then we will have mu z is equal to 3 mu b, b of eta. So if we do the experiment and collect the saturated magnetization and divide it by the mu b, then we make this gauge is mu b mu z, average mu z by mu b against to the b by t. Then the experiment point is shown here is the black and the hollow circle dot here. And we will find the theoretical value is the solid line would be very fit to the experiment 1. So that would be the excellent agreement between the theoretical result and the experiment data. Okay, so you can find if we go to the saturated magnetization, the mu z would be equal to 3 mu b. So shown here, you will find that the hollow circle is very close to 3, right? When we go to very high magnetic field or very low temperature. So in contrast, I will tell you that for some students from the chemical departments, sometimes you make the sample, but you are not sure what kind of the valence of the sample. Maybe you can make a test for in the to find the magnetization. If you do the experiment of magnetization, you will find the saturated magnetic moment, and from this saturated magnetic moment, you will find the actual valence of the compound, because the valence will correlate to the magnetic moment, as we just demonstrate how to get this this value 3 from the electron configuration. For example, if you have magnetite, sometimes magnetite have multiple valence that would be equal 2, equal 3, equal 5, and equal 7. For those cases, they have different electrons in 3D orbital, and therefore you can calculate magnetic moment for those valence and know the saturation mu z would be close to maybe 3, maybe 2, maybe 1, maybe 1 half, and so on. Then the experiment result will confirm which kind of the variant that you met in your compound. So I think this is the different way, except the X-ray fluorescence spectroscopy or NMR. There's a different way that you can extract the valence information from your compound. So that's the reason. Also, a second reason that we need to all of you to know the basic knowledge of the magnetism. Okay, any questions? No? Okay. So the final one of the theory is about the ferromagnetism. Okay. So the pairwise was the first to understand that under the domain structure or of the ferromagnetism and its fundamental atomic nature. So the atoms of the ferromagnet have net magnetic moment, and they will couple together to form a domain. So much of the previous discussed is applicable to the ferromagnetism, with one important modification. So you can imagine that why does those magnet or atomic magnet or spins will not interact to each other? They should interact to each other because they will create a magnetic moment. They may also create magnetic field, right? So in the ferromagnetism, we just modify a little bit. That is, we will not ignore the interaction in between these magnetic moments. For paramagnetic case, those magnetic ions are very dilute in the compound, therefore they will not interact to each other, which means they cannot make an effective internal magnetic field. But in ferromagnetic case, the interaction would not be ignored, so they will affect to each other by internal magnetic field, and this field will help those align together and become a domain structure. So this is the modification for between the this is the difference in the modification of the ferromagnetism to paramagnetic one. Okay, so a ferromagnet has a magnetic moment even there is no an external field. So this probably called spontaneous magnetization. So this observation leads wise to postulate the existence of an internal field proportional to the magnetization, and to replace the external applied magnetic B with the sum of external and the internal field. So this modification is like this. The B is an external field that we applied, but we imagine that there is an internal magnetic field called lambda m. Lambda is a determinate constant, and then m is the magnetization of the compound. So this internal field will increase with the increasing of magnetization, and the lambda is the proportional constant that connect the internal field and the magnetization. So in this description, they also explain why we have a hysteresis loop, because once the magnetization becomes larger, that the internal magnetic field will also increase. So if we remove the external magnetic field, but the internal field will not remove by the decreasing of external magnetic field. Therefore, we will not return to original state. In the original state, maybe the total magnetization would be equal to 0, right? So you can increase the magnetization by external magnetic field, but when we remove the magnetic field, it will not return to 0. Okay, so I will talk about that later, but you can just have a very a brief picture of this equation, of this modification. Okay, so we also use the old equations like this one, and the magnetization can write in this form. Okay, so this is the typical definition of valence magnetizations. So the valence magnetization is the sum of the average magnetic moments divided by the valence. Okay, and we can demonstrate in a very simple case. That is, if the J is equal to 1/2 and the G value is equal to 2, then this equation will become simpler. The M can be written as this form, and the eta is also 2 mu B by KT. And the Brillouin function will become simpler. The B 1/2 of eta is equal to 2 hyperbolic cotangent eta minus cotangent eta by 2. So in some algebra, we can calculate the magnetization. We can write the magnetization in this form, and in this case, if we talk about a spontaneous magnetization, we can just remove the B, which means the environment is lack of the external magnetic field. The magnetic field is solely coming from the internal magnetization. Then in this case, we can further reduce the mathematic form like this. Oops. The cos is equal to hyperbolic tangent cos by cos none. Okay, so in this case, we cannot solve. We can give you a certain solution of this equation, but we can solve it in a different way. That is, we can treat this equation as we have an equation called y equal to hyperbolic tangent cos by cos naught, and we also have an other linear equation is y equal cos. So this equation, to solve this equation, which means we would like to get the intersection between two equations. One is y equal to cos, the other is y equal to hyperbolic tangent cos by cos naught. So we are looking for its intersection. Okay, so this figure is the graphical solution of the equation. So this dash curve is the y equal to cos, y equal cos, and this curve, red curve, is y equal to hyperbolic tangent cos by cos naught. So the solution is these intersections. So we have two intersections. One is at the 0. The other is at certain point, something like here. And we maybe have no solution in some cases, like this green one or blue one. Okay. So where can we get the solution? We have a non-zero solution when the cos naught would be in between the 0 and the 1. And if we just extract cos naught to Tc, then we will define the Tc is equal to lambda n mu b squared by kV. Okay, so this Tc value would be very important because we can obtain the Tc value from experiment. Once you get the Tc, you will know the lambda value because the mu b is a constant, and the volume, you can measure the volume and the number of the atom inside this compound, and the Boltzmann constant is also constant. So all about the four parameters are already known. So you can measure the Tc from experiment and extract the proportional parameter lambda from experiments. So if you know the lambda, then you can solve many questions from the material. Okay. So this is the critical temperature we call the Curie temperature or Curie point in the ferromagnetism. So how to extract the Tc? You can go to the high temperature, which means that mv by n mu b is small. In that case, the hyperbolic tangent would be equal to x plus x times x to the 3 by 3. In the case that x is relatively smaller than 1. So in that case, we can write the equations as this form. So those prefixes are all constants. So we can plot the m against the t in this case. Okay, wait, So the x-axis is T by Tc and the y-axis is mv by n mu b. So when we started measure the magnetization at the low temperature, then we will find the mv by n mu b would be in this form, and we can fit it with the theory value and obtain the Tc value. Okay, so this is the ferromagnetic that at very low temperature. The very low temperature means the temperature is below than Tc. So when the T above Tc, the value is larger than 1. And at that case, all the magnetic point will be equal to 0. So shown here is the experimental value for the nickel, and you will find the fitting is quite good for the experiments. And by this way, we can use that to determine the TC. And from the TC, you can get the lambda value, which is the property of the compounds. Okay, so we already seen how the spontaneous magnetization varies with the temperature in the absence of an applied field. In the paramagnetic regions, T is larger than Tc, and we would like to know how the M varies with the T in an external field. So when the temperature is about the Curie point, the magnetization is small compared to saturation value, and this one would be rewrite like this form, and this form we call that is the Weiss-Curie law, or sometimes we call the Curie-Weiss law. This is the modification of the Curie law. So in the Curie law, we don't have the Tc, but in this case, we have the Tc because the internal magnetic field offset the magnetization comes to 0. So this is the measurement. The Tc represents the measurement of the internal magnetic field. Okay, in that case, we will also plot the inverse chi against the temperature and to obtain the Curie point. So I will ignore this. So in this case, this is the inverse chi against the temperature. We can fit linearly to this equation when we about a certain point. Then we will get the Tc from the intercept of this compound. And from the Tc, we can evaluate the lambda and know how the stress of the internal magnetic field. Okay, so this is an experiment demonstration for the application of the ferromagnetic theory. Okay, due to the time limit, so we will stop here. Okay, so please go back to the class next. I suppose it's next 2 weeks, because the next week will be Dragon Ball Festival. So that would be a national holiday. So I will see you in the next 2 weeks. Okay, so dismissed. Thank you for your attention.